C'est bon, okay. Okay, welcome everyone. So it's my pleasure to welcome back Hedy Attouch, who will be giving another lecture on the interface between dynamical systems and optimization. And today we'll be talking about combining dynamics and optimization algorithms with Tikhonov regularization. Yeah. Thank you, Hedy. Yeah.
So thank you, Boumediene. Very happy to be back in this nice community. And I'm going to talk about a topic which is very important and difficult topic, which is how to combine optimization algorithms with regularization methods. Right, we are going to give a rather general answer to this question in the case of a Tikhonov regularization. So here's the setting of a lecture. We are interested with convex differentiable optimization. In fact, we shall see that many of these hypotheses can be extended to more general setting. So the space, the state space is a real Hilbert space. X is the state of a system. Here is the square of a norm. Here is scalar product. And we insist working in general Hilbert space since we have in mind application to different domains. Optimization, finite dimensional optimization, classical, but also PDEs, also human sciences and economics. So there are many of a type of techniques I'm going to talk about. And the objective function is a convex function. We suppose that we have access to its gradient, but again, this can be extended to take account of errors and approximation and so on. And we suppose that the solution set, we call it S, solution set of a problem is non-empty. And this is a problem we're interested in. And our goal is to design, as usual, good, efficient first-order convergent algorithms, which mean algorithms for which you have convergence of the values and the bit rates to optimal solution. And fast first order means that we just want to use first order information, that is to say the gradient of f. There is, for most of the existing algorithms in optimization, there are two drawbacks. The first one is that in general, for a general convex function, without any further restrictive assumption, you have only weak convergence of the iterates to a solution. Okay, in finite dimensional space, okay, it doesn't make any difference, but in infinite dimensional space for PDEs, for example, for inverse problems from physics, having only weak convergence is a drawback, since this means oscillations. This is the first drawback. The second drawback is that in general, you produce iterates which converge to a solution, but you don't know which solution you obtain. Of course, and considering the case where the solution set is not reduced to a singleton, right? Depending, for example, on the initial data, your first initial state, you obtain different, when you change it, you obtain different solution. And this is not completely satisfactory. In general, you want to obtain a solution with some favorable properties. For example, you want to obtain a solution which is as close as possible to a desired state. For example, if you want to improve a plane, yes, you want to improve it, and so you have some function f you have some inverse problem to solve, and you obtain let's say you solve your problem, you obtain a plane, but if your plane you obtain is very different from the one you start from, it's completely it has completely no interest. You want to improve the initial shape you have for your plane. You want to find a plane which is as close as possible to the initial one. Okay, so to say that you have an algorithm which converges to a solution, in many situations, this is not very satisfactory. So in this lecture, we are going to explain how to correct these two drawbacks and design first order convergent algorithms for which you have both norm-convergence of the iterates and convergence to the minimum norm solution. Minimum norm solution, you can easily change it to the solution which is as close as possible to a desired state. And this is, as we shall see, okay, a very subtle equation to solve in such a general setting. And in this lecture, we are going to completely solve this problem, I think, in a satisfactory way via dynamical system. Since attacking the problem directly on algorithm is very, very difficult, you see. But dynamical systems are more flexible. They give you some physical intuition, and it's easier because you have the help of the differential calculus, integral calculus. It's easier to develop, let's say, Lyapunov analysis. And the dynamic we are going to use for solving this equation is the following dynamic. At first glance, it looks quite complicated. In fact, it's not. At least numerically, it gives rise to quite simple algorithm. So it's a second-order differential equation. So you have inertia. You want acceleration, you want fast methods. So you want to design fast method with the help of accelerated methods. So here is the acceleration. Here is the driving force, the gradient, okay? And here you have a damping. As I explained in the preceding lecture, you have two types of damping. There is a viscous damping here, and here is a geometric damping, which is important in order to attenuate the oscillation. And here is the Tikhonov regularization term. See, in the Tikhonov regularization, we take the parameter in front of the Tikhonov term, which goes to 0 as t goes to infinity. Why? Since we want to preserve the equilibria, you see, if we take epsilon fixed, okay, that's fine. You have a strongly convex function, but you change the equilibria. Maybe close, but you change it. We want to solve exactly this problem, right? We want to solve this problem. We take a regularization term here, Tikhonov regularization, with a parameter which goes to 0. And the new thing, which has been discovered very recently in the last month, it's a fundamental idea, which is that in order to have a good method, you have to have a link, a very precise link between these two parameters. The parameter, the Tikhonov parameter, and the viscosity parameter. Here you see this is fundamental. You have to take here epsilon of t and here square root of epsilon. This is a parameter, it's not important. Usually you take it strictly greater than 2, that's okay. That's very important. And I'm going to explain this. And this gives a new light, for example, Nestrov method. This is better than Nestrov method. I shall explain you in a moment in what sense. So you may say, okay, maybe physical, this is okay, but now explain why you can. The first thing is I give you a model example of this dynamical system. I want this coefficient, Tikhonov regularization, to go to 0. So, for example, I take some power of 1 over t. So when t goes to 0, this goes to infinity with r, the parameter r, which is strictly positive. So here is 1 over t power r, and here is a square. So it's t power r over 2, and you have these two terms. You see, and the tuning of a parameter is very simple. You just ask r to be strictly less than 2. The parameter here is strictly greater than 2, beta strictly positive. So it's a very simple tuning, you see, the continuous form. And you have, that's a trick, fantastic, you see. This is the result of more than 20 years of research, you see. Within the same dynamical system, you have 3 fundamental properties. You have fast convergence of the values. I'm going to return on that. You have fast convergence of a gradient toward 0. okay? And you have strong convergence of a trajectory towards the minimum norm solution. Independently of the initial data, whatever the initial data is, you are sure that the trajectory converges strongly towards the minimum norm solution. Let's comment it a little bit. Why it's, in some sense, it's optimal. In fact, to be really optimal, okay, in the sense of Nesterov, you have to take R equal to 2. Because if you take R equal to 2, you have 1 over t squared, and you know that this is the optimal rate of convergence in the case of a general function, right? So here we have not 1 over t squared, but we have 1 over t power R. But R can be taken arbitrarily close to 2, which means that if you take R equal 1.999, okay, you have the same rate of convergence as Nesterov, you see, right? And moreover, if you take, you see, R equal 2, 6 minus 2, 4 over 2, so t squared, this is the optimal rate of convergence for the gradient. Right. Now the next objection you may have is, okay, that you have deviation. That deviation, you see, is something, you know, is something difficult to handle with. And in fact, I answered this question in the previous lecture. In fact, deviation helps. It's not a complication. This makes the dynamics simpler. There are many reasons for that. The first one is that for a numerical point of view, it's completely free. Because this term, you see, you consider not deviation, but the action of deviation on the velocity. And this term is just a derivative of a gradient of f at x of t. So when you discretize this dynamical system, what appears is just this correcting term. You see, if you drop this term, this is the classical Nesterov algorithm. See, you have just this correcting term, and this correcting term is free, since you have just to keep memory of a gradient at the preceding step, right? You already computed this term, so you have just to keep memory of this term, and you just add this correcting term. So from a numerical point of view, it's completely free. And for the corresponding algorithm, you have the same type of result properties as for the continuous dynamic. This result concerns the case without the Tikhonov regularization. And in the case of a Tikhonov regularization, you have quite the same type of result, but this is a question which is in progress. Right, and the important deviation is partly convincing in the case of ill-conditioned convex optimization problem. Here, it's really badly conditioned. If you work with a usual Euclidean distance, this is a very badly conditioned function. If you use Nesterov method and the Suboy-Candes dynamical version of Nesterov method, you have this trajectory in blue with this wild oscillation, so it's completely awful, you see. By contrast, if you consider the dynamic with the Asian-driven damping, now you work with a right metric, which is in the same spirit as the Newton method, and now you have a very nice trajectory, which is in red. You completely forget about these wild oscillations. So deviation is very important, and the message of this lecture is that deviation is very important, and the Tikhonov regularization is also very important. And it's the first time that the two of them are considered within the same dynamic, you see, and that you obtain the three preceding fundamental properties. The result I'm going to report, they've been obtained in very recent papers. Here is the case of Tikhonov regularization without deviation. It has just appeared in Journal of Differential Equation. And when you add deviation, this is a paper which has been recently submitted, and this is available in arXiv, and that's the one I'm going to report. on. And concerning the algorithmic aspect, you can find them in the math programming paper published a couple of 2 years ago. So I'm not going to enter into technical aspects. I'm going to recall a very simple fact, a very nice result concerning the Tikhonov regularization. So the idea of Tikhonov is the following. You have a general convex function, okay, and the idea is to approximate and to improve the function just by adding this correcting term, which makes the function strongly convex. See, when you have epsilon strictly positive, you pass from a general convex function to a strongly convex function. And strongly convex function, okay, they are nice from the optimization point of view. If you write the optimality condition, you have this, and we call X epsilon the solution of this minimization problem. And what we call the viscosity curve is the curve which to each epsilon associate X subscript X epsilon. At this point, there is no dynamical system, just the static point of view, the point of view of the approximation of a Tikhonov approximation. And the properties of a viscosity curve, which are very important in this topic, are the following. The viscosity curve do converge strongly to the solution, the minimum norm solution. Okay, and that's the origin, you see, of this property, of this Tikhonov property. We are going to prove this in a moment. And the viscosity curve remains in the ball centered at the origin of the radius norm of its star. And about the differentiability property of the viscosity curve, in fact, there is a difficulty because even if f is a very smooth function, in general, this curve is not differentiable. See, it's only a local Lipschitz on this interval, which means it's Lipschitz continuous on every interval delta t with delta strictly positive and t finite. It's locally Lipschitz, and you have a bound of this type. You see, and if you integrate this quantity, this is infinite when it's close to 0, and epsilon go to 0 is fundamental, which means that this curve, the viscosity curve, has not a finite length in general. And this is a source of difficulty, and which makes the Tikhonov regularization not such an easy object to deal with from a mathematical point of view. And the idea between Tikhonov and to give a proof is much more general. See, instead of taking the square of a norm, you may take any arbitrary function g. So you consider f minimizing f plus epsilon g. And in a general topological space, you suppose that the two functions are tall logarithmic continuous. So is the topology you work with. And for each epsilon, you have a solution of this problem, and you assume that this trajectory is relatively compact with respect to this topology. Then in this general setting, you have convergence of a value with this rate of convergence, and every limit point of total limit point of a sequence satisfies this hierarchical minimization. Okay, it minimizes G over the set of solution of the problem. When you have G is equal to 0, you minimize F, and by introducing this the regularization or perturbation term, when epsilon goes to 0, you end up with a solution which minimizes G over the set of solutions. This is a hierarchical minimization, and this result shows you the big generality of this type of result. You just need a topological structure in order to give a meaning to this kind of result. And if you want to get an intuition of this result, there is an easy way to do that, is to consider the equivalent penalization formulation. You subtract the infimum of f in order, this doesn't change the minimization problem, okay, in order to have a term which is non-negative, and you divide by epsilon. This doesn't change the minimization problem, and now you turn with this problem. And you see that when epsilon goes to 0, this term increasing to okay, it converges to the function which is equal to it converges to plus infinity. It's increasingly converging. Here it's decreasing, and plus infinity if you are not in the solution set, and 0 if you are in the solution set. So at the end, you end up with a minimization of G on the solution set, and that's exactly the hierarchical minimization principle. So the idea is very simple, and it's easy to catch via the penalization formulation. And I've been very interested with this kind of ideas in the 20 years ago, and because I discovered that there is plenty of problem situations from optimization, mechanics, physics, where you find this kind of structure. Here is the classical Tikhonov regularization of inverse problem. Here is the van der Waals-Canillier model of phase transition. See, what's classical is the Gibbs formula, where you have the potential with two local minima, which correspond to each phase. By introducing this term, you see, and when epsilon goes to 0, in fact, you find the right interface between the two phases, which is a phase with a minimal surface. So this makes the link with the minimal surface theory. In linear programming, when you add this log barrier term, you end up with, so you have an interpoint method, and you end up with the center of the optimal phase. In fact, in this case, it's the analytic center. And here you have a situation where you have weakly coupled system, domain decomposition, and so on. So this is a topic which is a very, very important topic with application in many different domains. So before coming to the state of the art, I'm going to describe you the progress of theory in the last decades. So first works concerning the dynamical system. Now, you want to introduce a Tikhonov regularization term into your dynamic and hopefully obtain a trajectory which converges strongly to the minimum known solution. So first, you start with the simplest dynamic, which is the steepest discontinuous steepest descent. And a lot of people were interested with this topic because it's very simple, you see. It's very simple to state. And curiously, it's not so easy to solve. There is a lot of papers. I have not time to cite all of them, but a lot of papers consider this problem. But in each case, they did some restrictive assumption on epsilon. Usually, they need some differentiability on epsilon and so on, epsilon decreasing. And it's only in the paper by Cominetti, Pepucchi, and Sorin, Journal of Differential Equation, 2008, that they really find the theorem with minimal assumption on the Tikhonov regularization term. In fact, you just need epsilon to be a non-negative measurable function, measurable in the sense of Lebesgue. You see, you don't need, even not continuous, and you don't need anything, just measurable. See, it's difficult to construct functions which are not measurable. You see, so no regularity on epsilon. Just ask epsilon to go to 0 and not too fast. Not too fast is measured by the fact that this integral is plus infinity. So the critical case is 1/t. See, if epsilon goes to 0 too fast, it's just like here you have epsilon. So you have only convergence to a minimizer and no more. If you want this Tikhonov regularization term to be active, this coefficient has to go to 0 not too fast. Not too fast means that the integral has to be plus infinity. If you take epsilon of t equal 1/t squared, so this is finite. If you take epsilon of t equal 1/square root of t, it's okay, right? This is plus infinity, and then you have convergence to minimal norm solution. And clearly the most intricate case is the critical case. You see, is 1 over t. It's the smallest, so the smallest perturbation of this dynamic for which you have this convergence property. And you can extend this to a more general coupled dynamical system. It just gives you the proof, you see, because it's very challenging. It's a very simple proof, but a lot of people tried to find this proof and they didn't succeed. And so what you do, you call f epsilon the Tikhonov regularized function. So you can rewrite this dynamic in this form. And you take as a Lyapunov function just the distance from x of t to x star. X star is a minimal norm solution, right? You derivate this, okay? Then you replace x star, x dot by this expression, and then you use the strong convexity of the Tikhonov regularization, and then you end up just 2 lines proves you end up with this inequality, okay? And this inequality, you just use a classical Grandval-like lemma. You integrate this and use that x of epsilon of t goes, since epsilon of t goes to 0, we know that the viscosity curve converges to x star. So this makes theta of t go to 0 and gives you the result. Right. So now let's come to now inertial method. Okay, and let's start with the simplest inertial dynamics. It's Polyak EV ball. If you drop this term, okay, this is the classical Polyak EV ball method. Gamma is the damping coefficient, which is a strictly positive coefficient. And this result we obtained with Markovits-Zarnecki in Journal of Differential Equation 2002. And but in that case, we need to assume some additive, let's say restrictive assumption at epsilon. We assume also that epsilon is non-increasing, it's non-increasing, and its derivative goes also to 0. And that's a classical slow parametrization assumption, is to say epsilon goes to 0 not too fast, and then you have this result. And the proof is much more complicated than for the steepest descent. In fact, the proof, we are very proud with the proof, since we had to combine Lyapunov analysis with geometric argument. That is to say, in the Lyapunov analysis, you make appear a term which has a different sign depending on the domain in which you work. So we had to divide the space into different domains, and each domain, we studied the behavior of a dynamic. You see, it's a very classical idea in a dynamical system. And so we had to combine Lyapunov analysis in order to obtain this result in full generality. And since this result has not been improved, for example, it's an open question. Can you prove that without assuming that epsilon is differentiable, non-increasing, and the derivative goes to 0? Just assuming that epsilon goes to 0. I don't know. And so this is an open question. Right. Now we come with the state of the art. And here is really a new idea. At the beginning, in order to obtain fast convergent method, we naturally were thinking about the Nesterov method, right? But, okay. And we didn't completely succeed because, as I said before, in the case of Nesterov method, it's an open question to know if you are able to introduce a Tikhonov regularization term for which you have strong convergence. You see, in our model example, you see, Nesterov corresponds to R equal to, when R is equal to the coefficient in the Suboid Candace model of Nesterov, and if that R equal 2, we are not able to prove the result. You see, we have to take R strictly. So it's an open question to know if with Nesterov method you can obtain this result. We didn't succeed, and that's what we say, that maybe Nesterov is not the best. So we had another idea, which I think is better, which is not to work with Nesterov and Suboid Candace dynamic, but with Polyak, with EV ball, but with the EV ball for strongly convex function. That's the fundamental idea in this. If you just remind something of this lecture, the good dynamics is the EV ball method of Polyak for strongly convex function. And in the case of strongly convex function, you have exponential convergence rate. You see, the Polyak EV ball is a good method, let's say, only in the strongly convex case. But in the strongly convex case, it's an excellent method. It's better than Nesterov, you see, since in that case, you have exponential convergence rate. And what's important in order to obtain this result is the adjustment of the viscosity coefficient. If F is mu strongly convex, then you have to take the coefficient equal to square root of mu. You see, it's here that the square root passing from mu to square root of mu does appear, you see. That's a fundamental result. If you want to apply this result with F mu strongly convex, then you need to have a coefficient which is of order square root of mu. And recently, in 2020, we extended the result of Polyak just by adding the variation. Here, it's not very complicated. And you have exactly this, the same type of exponential convergence result for the function and the gradients. Right. So that's the idea. We're going to use this dynamic. And this dynamic, what we're going to use, now we take F, a general convex function, okay? So we are not going to use this dynamic with F, a general convex function, because F is not strongly convex. So in order to have a strongly convex function, what we use the idea of Tikhonov. In this dynamic, we replace F by its Tikhonov approximation, okay? F epsilon of T, online regularization. You see, at time T, we replace F by F index epsilon of T, okay? The Tikhonov regularization is depending now on T. So you replace F by this expression at time T in this dynamic. And what you observe is that F epsilon of T is convex to a coefficient equal to epsilon of T. So here you have to replace square root of mu by square root of epsilon. And gradient of F epsilon is gradient of F plus epsilon x of T. So you make appear, you see, this fundamental property, okay, the tuning, respective tuning of the Tikhonov and viscosity term is here epsilon and here square root of epsilon, okay? Right, in fact, you can also make the change here, but this doesn't, if you replace F by F epsilon here, you make it here epsilon x star and epsilon x star. The epsilon is negligible with respect to square root of epsilon, so it doesn't change the dynamic. It's a variant, interesting variant, but essentially the same. So that's the origin of the dynamic we are going to consider, right? So you have this dynamic, and then you proceed with the Lyapunov analysis. And Lyapunov analysis, I must say that it's quite technical, you see. At this time, we succeeded in the Lyapunov analysis in the continuous case. See, in the discrete case, I'm very optimistic about the fact that we will be able to extend it, but it's not so easy, see? And the Lyapunov function, see, here is the, you see, you replace F by F epsilon T, and here you have to take x of epsilon of T, because x epsilon is the point where this function attains its minimum. So if you want this to be non-negative here, you have to take this point. So you make appear the viscosity term, the viscosity curve in the Lyapunov function. That's why you need some regularity on the epsilon of t. And here you have this quite classical anchoring term, here the, the velocity and gradient. And what we did, you derive this, you use the equation, the convexity of F, and you end up with just like you see the proof of exponential convergence of value for the Polyakov ball in the strongly convex. Yes, you end up with a differential equation. You see, E dot of t plus mu of t E of t plus a coefficient. Here, this is non-negative because we take delta. We take this parameter strictly greater than lambda, right? And lambda is the parameter which appears here. So this is non-negative. So we have this differential equation. So you can imagine that you are going to integrate it. And here we have terms, you see, second member, coefficient mu of t, they just depend only on epsilon, rather complicated way, and then the different parameters, right? I'm not going to integrate it in the general case, we did it, but just say that from this you obtain estimate of a rate of convergence of E of t towards 0, and from the rate of convergence of E of t, very easy, it's a simple lemma, you obtain rate of convergence of the trajectories. And since this goes converge strongly to X star, you obtain that X of t converges to X star. And so I return to the model example in the case where epsilon of t equal 1 over t square, t power r, then you can compute very easily all the ingredients of this Lyapunov analysis, and you obtain these simple results. Here, a rate of convergence of values of a gradient, and strong convergence of X of t, and you have rate of convergence for all of them. At this point, it's interesting to make some comments about the respective rate. It's the first time you see that within the same dynamical system, you have these three properties. Up to now, people were able to obtain one of these values for a dynamical system. But if I want to have the other property, they have to change the dynamical system and so on. So it's okay. It's a big challenge to obtain these three properties within the same dynamical system. If you take any trajectory of the system, these three properties are satisfied. And to understand the difficulty of the situation, just observe what happens when R goes to 2. R equal to 2 corresponds to Nesterov method. You have 1 over t squared and 1 over t, the Suboid-Candace model of Nesterov method. And when R goes to 2, so you are very happy with the convergence of values and convergence of gradient to 0, but you are not so happy with the convergence of trajectories to the minimal norm solution, because when R goes to 2, this coefficient goes to 0, you see? So at the limit, you lose the convergence property of the trajectory to the minimum norm solution. That's what I say, that Nesterov maybe is not the best. It's better to take R close to 2, very close to 2, but strictly less than 2. And if you do that, you have these three properties which are satisfied. For R equal to 2, we are only able to obtain these two properties. Okay, it's an open question whether for Nesterov you are able to obtain the three, but I have some doubt about that. But it's an open question, it's state of the art. Another interest of the radiation damping is that this dynamical system, which may look quite complicated at first glance, in fact, it's a very sympathetic dynamic. This term, you see, helps. It helps. It doesn't make the dynamic more complicated. Indeed, it makes the dynamic simpler. This can be understood, for example, from a mechanical point of view, because if you have not this term, when F is non-smooth, you end up with elastic shocks, and elastic shocks in the non-smooth case, this is something awful. But this term regularizes the dynamic and turns, instead of having elastic shocks, you have completely inelastic shocks, which is far simpler. And in fact, in this dynamic, each term comes with its derivative. Here you have x dot, x dot dot. Here you have a gradient and derivative of gradient. So in some sense, you can integrate this differential equation and have an equivalent first order dynamic via the introduction of an auxiliary variable, which we call it y. See? And now, this is not the Hamiltonian formulation of a problem, since if you take the Hamiltonian formulation, you still have the variation. See? Here, there is no more variation. There is only the gradient of f which enter into this dynamic. So it's a gradient method in the product space plus a linear, non-autonomous linear perturbation of a gradient term in the product space. So this is a very nice, very simple structure. And the most important, since you have this equivalence, is that you can replace f in the case of a non-smooth function by its subdifferential. You just replace f by its subdifferential, and this dynamical system still makes sense for a non-smooth function. You may even consider this dynamic in the case of smooth non-convex function. This still makes sense and still has nice properties. And this dynamic, you can apply it, as I said, to a study of damped shocks in mechanics, and you can do numerics, efficient numerics with that. This has been done, for example, by Castera, Bolt-Favored, Powers, deep learning. You published a nice paper in Journal of Machine Learning Research, 2021, and you can apply it also to a structured convex optimization problem and design nice forward-backward algorithm. This has been recently published, Numerical algorithm, 2020. Just to convince, this is not, you see, a real situation, just academic situation, illustration to see, to illustrate the result. We consider in R2 function, you see, which is not strongly convex. You have a continuum of solution, which is this line. The element of minimal norm is this point. And we have just computed the trajectories of this system. And we have compared the system with and without the variation. With variation, these are the continuous line, and with without variation, in all cases, it's Tikhonov regularization, but in continuous line with variation, in dot line without variation. And we observe that without variation, you have this oscillation, wide oscillation, which are okay. So variation is helpful, and also we observe that we make vary the coefficient R when R, the coefficient R, the exponent goes to 2. We have a better convergence rate of the values, but we have a poor convergence rate of the trajectories. Right, and I'm going to end this lecture with some comments, and we have time to talk and discuss about that. So just a summary of the result. So we have described the dynamic perspective on the accelerated optimization algorithm. The new idea is that we're able to combine in the inertial method Hessian-driven damping with Tikhonov regularization. If you do that, you have both fast convergence of values, fast convergence of gradient over 0, neutralization of the oscillation, and strong convergence of trajectory to minimum norm solution. So, okay, it's optimal. You see, what to do best, you see. So now the challenge, the big challenge, is to to take advantage of this result to develop it in an algorithmic setting. This is a lot of work. In my opinion, there are work for many years, and but fortunately now we have a mathematical background for that. You see, without the help of dynamical system, it would have been very difficult to have this real optimal result. You see, it's the result of more than 20 years research. You see, it's not the fact, but you see, when we start thinking about this kind of things 20 or 30 years ago, this was not clear at all. I mentioned an interesting paper, Rosasco and Villa. They have a series of interesting papers where they consider the algorithmic aspects and using iterative regularization in machine learning. So you can consult this kind of papers, interesting ideas. As I say, the case of Nesterov is a critical case. It's interesting to deepen this situation and say, okay, that many of these ideas can be extended to non-convex, non-smooth optimization. Then you have to consider splitting algorithm, and so on. There is another question, something which puzzled me, is the following. I think it's an important question, but I have not a complete answer to that. You see, the dynamic we consider, there are non-autonomous dynamic. This is a non-autonomous dynamic. That is to say that we have terms here which are function of time, see? Okay. These are control, you see? These are control which are given as a function of time. It's open loop control. If you see them as a control term, it's open loop control of a dynamical system, here inertial dynamical system. It would be nice to have a closed loop version of this dynamic. Closed loop means that instead of taking epsilon as a function of t, you want epsilon to take it as a feedback, as a function of a state of a system, the state, the velocity or gradient, but not as a function of t, but as it's a function, a feedback, it's a function of a current state of what you can observe of your system. And so to main advantage, if you consider a closed loop damping, is that now you have an autonomous system. And the mathematical theory for autonomous system is much better and much simpler than for non-autonomous system. And what happens is that for Tikhonov method, there exists a closed loop version of Tikhonov, which is the Ogazo method. And I have not time enough in order to explain in detail what is Ogazo method, but Ogazo method does provide exactly the same thing as Tikhonov in an autonomous way. The problem with Ogazo method is that at each step, you have to perform an operation which is not as simple as with the Tikhonov method. You have to take the projection on the intersection of two half spaces. This is not a very difficult problem. You have explicit formula for that, but if you have a large size problem, and if you have to do each time this kind of operation, this is not so good. So, but Ogazo method, I discovered recently that Ogazo method, you can see it as a closed loop version of Tikhonov. They have the same structure. And you can consider also extension to monotone inclusion, regularized Newton method. In fact, the Tikhonov method is not limited to minimization problem. It also works with monotone operators. And then you can enter into stochastic version, introduce noise and stochastic gradient method and so on. And there is a lot of things to do. And I think there are for years to work on this kind of question. So I thank you for your attention. That's okay.
Yeah, thank you very much. Thank you. Any questions or comments?
Yeah, about the last, maybe you want to elaborate. When you talk about stochastic and noise, I'm always interested in the interaction or the complication via noise interacting with the regulation.
Yeah, you're right. This is a difficulty. You're right. Yes. Yeah.
So this sounds like very highly nonlinear.
Yeah.
And I'm a bit inspired by your iterative, incremental, and interactive that you had by Vosato.
I know the difficulty. What I can mention to you, there has been recent papers by the team by Villa, Rosasco, Guillaume Garrigos. They've been thinking deeply about the question of using Tikhonov regularization for noisy problem, and so they succeeded in some sense finding what's the right tuning of a Tikhonov. In that case, you have not to make the Tikhonov regularization go to 0 as I did here. But this is a subtle question. I'm not an expert of that, but do return to these papers, and they did a deep research on that. It's not an easy question, and I agree that in the case of noisy problem, you have not to make the Tikhonov regularization go to 0.
I didn't catch the references. Maybe you can put them in the chat or the last one. Or...
Sorry?
The references that you mentioned in your answer, yeah. I didn't catch them. I want to look at them.
Okay.
Is that possible to get them in the chat or?
Yeah, for sure. In fact, this paper, you can find it online. You see, it's in archive or something like that. It's very easy to access to it.
Yeah, I think he's asking about the other ones. I mean, do you have like the list? I mean, can you provide the list, or maybe you can send it to us by email, and then we'll get it. Yeah. All right. Yeah. Thank you. Yeah.
Thank you.
Any other questions or comments? Yeah. Okay. So I had a question actually. So about application of these things to machine learning, like because this seems to be like a very important result here. Like if you take, like, for example, a simple neural network, and then you want to train it, and then you apply this kind of result. I mean, what would you get in practice? I mean, would you be able to find like an optimal architecture or find parameters of the neural network and guarantee conversion?
You see, depending. You see, either the problem is convex or non-convex.
Yeah. Usually these problems are non-convex, right?
Yes, I agree. So in this lecture, it's convex, you see. Non-convex is much more complicated, you see. And the general theory for dynamical system for non-convex optimization using Kurdika-Loyazevich theory, we use autonomous dynamical system, see?
Yeah.
It's we are not able to, we have not a general theory of a dynamical system in the non-convex case in the non-autonomous case, you see. Combining in the non-convex case, combining dynamical system with approximation, it's a subject, you see, a very difficult subject. It's research. You see, the current research, there doesn't exist a general theory in that case.
Yeah. What about like the other question around? I mean, for example, so you put yourself in this kind of framework. I mean, what do you think would be like a simple architecture where these results apply? So here, okay, like a general case, maybe it's non-convex all the time, but what about the other way around, or which would be like a simple neural network where this kind of results apply? I mean, it would be like convex, but then
Yes, you have. I gave examples.
Yeah, I saw the examples, but I don't.
This kind of problem.
Yeah.
Yeah.
See, actually, this is what I'm trying to see.
Yes, in fact, in general, for real problem, you have some intuition, you see, of what you're looking for. So the skill of the engineer is to add a regularization term, which is nicely designed. You see, you add a term. You don't want in general, you don't want the term which has minimal norm. You see, you want to obtain a solution as close as possible to some what you think is a good solution of your problem. And in that case, you see, adding this term, it has nice effect on the solution, you see.
Yeah.
But, you see, this is a general framework, you see. This is for Tikhonov regularization. But in fact, the idea we are developing here, they are much more general than Tikhonov regularization, you see. You can consider them with this kind of structure, you see. And you can even more consider general approximation methods. And for example, you can use some penalization term on the constraint. You may use diminution of dimension of the space on which you work. You may use truncation on the, if you have a sum, you see, of in your objective function is written as an expectation, as a sum. You can make truncation on it and so on. You can use a lot of approximation method for which you use this kind of ideas, you see. But you have not a general theory to explain all of these things together, you see. But what I say is that there is the same mathematical structure behind them. And in this lecture, I'm going to explain just the case of Tikhonov regularization, you see, which, as I said, is already involved, you see. But you can develop the same type of idea for many different types of approximation, you see. You have a difficult problem.
Yeah, okay. There's some noise. Yeah, I mean, there's like some speaker. He was unmute here.
So you have a difficult problem, and the idea of the approximation theory is okay. It's just like a big mountain. You see, you are not going to attack the big mountain directly. You see, you want to have steps. And you see, you approximate it by something which is not so high or which is smoother, and so on. So the idea is how to couple the usual algorithms you have, minimization, optimization algorithm, with approximation method. And the point is how to tune the regularization parameter. You see, you have an algorithm at each step K, at stage K, you have to tune the approximation parameter in the right way depending on K.
Yeah.
And this depends, you see, on the type of approximation, the type of problem you want, etc., etc. Here you have a rather well-developed theory in the case of Tikhonov. In the case of Tikhonov, we have well understood that. And but if you have a typical problem, then you can pick up some ideas from here and develop it in your own framework.
Yeah. No, I like the idea very much. But usually, like what we do in practice is that you just observe. I mean, if you are converging, then you keep the same regularization, and then if you start diverging, then you reduce the lambda, or sometimes, and then but it's very slow. You increase it, but you do it by hand. You know, you put it in the code.
Yeah, usually people do it by hand. You see, the challenge is to have a mathematical background for that. You see, and this is you see, mathematical background for that, because the reason is that it's very subtle, you see, it's not easy mathematics. It took, let's say, 20, 30 years of effort before reaching this kind of result, you see. And there are applications not only in machine learning, but in all domains of sciences, physics, mechanics, biology, economics, human sciences. And in all these domains, you see, you have a small parameter, different level of energies, and so on and so on. And you want to understand what happens.
No, it's nice, actually. It's yeah, very nice. Yeah, thank you. Yeah, okay. Any other questions or comments? Or? Okay, thank you, Hedy, again. So, so maybe like if there'll be like another lecture whenever you are free, like some time, like in the next academic year.
Okay.
Yeah, okay. Thank you very much. Thank you.
So thank you very much.
Yeah, thanks a lot. Bye bye. Have a good day. Thanks. Take care. Bye bye.